So bonjour à tous, good morning, thanks for coming to episode 2 of Gravitational Waves in a Nutshell. So on the screen last week, a quick recap, since I didn't know when I put it there, but since there may be a couple of new people. So in general relativity, curvature propagates like a wave. Curvature means the Riemann tensor at the speed of light. These gravitational waves are transverse, like the electromagnetic field, and they're quadrupolar. However, you may call them spin 2, as in a rotation of 180 brings them back to themselves. They are emitted at the leading order by time-dependent mass quadrupole. It cannot be monopole because that's conserved, that's mass. It cannot be dipole because that's a momentum also conserved. And as we've seen with the LIGO-Virgo observations, they cause the accelerating spiral of binary stars, since binaries are accelerating in the circular orbit or quasi-circular. That creates gravitational waves, which carry away energy from their orbital energy. How do we see them? We can either think of them as tidal forces. A tidal force is one that doesn't move the center, let's say, but moves the ends of a system with respect to the center, like tides on the Earth. Or equivalently, you may think that, say, the mirrors in LIGO are not actually moving. They stay at the same coordinates, but it's the distance between them that changes. That's the principle of detection that's used in all modern gravitational wave detector. And last, actually, we didn't see it last week, we see it this week. They carry energy momentum, but it can only be localized approximately. And that's because of the equivalence principle, right? You can always go to a reference frame and to a state of motion where you don't see gravity. If you do that, you wouldn't see the local energy, but if you look a little more broadly than that, energy comes back, and that's what we detect with detectors. So there's a range of different detectors that have been built and deployed. They're somewhat adapted to the sources that they target. The ground-based detectors based on that use interferometry target stellar events, things like neutron stars and black holes. In the future, 2034 plus 35 now, maybe LISA will target a millihertz range, and that's where we see either binaries that are farther away or supermassive black holes. And currently, we have experiments that use the galaxy really as a detector by using distant pulsars as clocks and monitoring the time of propagation of the pulses to Earth. And those are pulsar timing arrays, which work at the lowest frequencies of periods of a year or a few years. Even lower, there's effect of gravitational waves on the CMB, and for that you need a different different course. Okay, so this is the movie that didn't work last time. It's a decent representation of what happens in LIGO, right? And so you're splitting light, you send it around to different arms. Doing so accretes a phase delay due to the difference in length between the two arms. And now, if at the output port of the detectors you see nothing, then that means that I think I should show nothing the movie in a second. That means that it means there's a perfect destructive interference and therefore no power. But if the arms are a bit different, you get some power out. And this is your, very cartoon description. So I'll go a little more in depth. Since these are, as a theoretician, I have to appreciate the wonders that experimentalists do. Also, it took them like 50 years to get to this point, right? From the first ideas to realization. Actually, it's interesting to look back to where the idea comes from, right? Of gravitational wave interferometers, and I can quiz the audience. So this is probably too small for you to see, but can you guess or remember what that is? Yes, that's a Michelson-Morley interferometer, 1887. Okay, so it proved that there's no ether. Okay, so that the speed of light, not of life, speed of light is something in Paris is very fast, but and it's slow in Italy. But no, the speed of light is constant. no matter the direction. So what happened? However, from Einstein's 1916 paper about the linear perturbations of his equations of general relativity, up into the 50s, there was still quite a bit of confusion about the reality of gravitational waves, because you know, because of general covariance, general relativity allows you to change coordinates. Okay, so that you may call it gauge freedom. Changing coordinates lets you cancel out some effect, at least apparently. So there were many who thought that the gravitational waves were actually just a manifestation of coordinate freedom. So basically there were waves of coordinates and not real waves. So it was really Pirani, Felix Pirani, who was maybe Polish, I'm going to say. So I should look it up for you later. Who did the analysis using the geodesic deviation equation that I showed you last time, where Riemann actually creates this tidal motion of a circle, say, of particles, idealized circle of particles. So, so that pointed to the fact that Riemann curvature, and therefore also waves of Riemann and wave of curvature, would have a measurable effect, that of moving nearby masses relative to each other. And at this Chapel Hill conference in '57, which had was a big one, right? With all the big people, he presented this, and it was Bondi who actually said, well, but what if we add a dashpot? A dashpot is a friction device. It's something that in a mechanical system absorbs energy, basically, when you move things through it just by friction. So you move in this, the masses relative to each other, you have something that constrains them, you absorb heat. So that was the argument that showed that gravitational waves can carry energy, and then they can be detected. Okay, so interestingly, this argument is usually attributed to Feynman, right? The ring argument and so on. But if you look at the like historians of gravity have done, if you look at the proceedings of that conference, he spoke later and mentioned that idea, but it was brought up by these two guys, Pirani and Bondi. So Joe Weber, whom we saw last week, his picture, saw this, and he said, okay, we can do, started thinking about resonant mass detectors. So think big masses that will therefore vibrate when you have gravitational waves. And that led into his experiments, his claims of detection, and all that. But others, and in particular Wise, Ray Wise, who was later one of the LIGO founder, realized that that actually the best way to detect something like this, relative motion of masses, would be an interferometer, because that's exactly what it does, right? And he thought that with that, he could obtain a much better precision than with any other way. So Wise actually put out a first white paper, I think, with a prototype, with a model in 1970. Of course, like with everything in physics, when you do something, the Russians have done it already, right? So there is a paper by Gershenstein and Pustovoit, which I think is 1962, that also basically shows proposes the idea of an interferometric detector. And as far as we know, it was not known at the time to the Americans. That's also typical. We're doing it. Never mind. However, so there's a, let me see what I have here for a moment. So what's the complication to doing this? That in Pirani's scheme, you need freely falling masses. Okay, those are not freely falling masses. Those are things that are bolted on top of a table, and therefore a good reason, because when to arrange for interferometry, you need to have the exact geometry so that you put fringes of light, which are what 1 micron. Okay, exactly on top of each other, and you need to keep that configuration. Doing interferometry with freely falling masses is hard, especially on the Earth. But it's worth discussing this basic thing, because if you give a talk, a public talk, and want to mention gravitational waves, This is something that Ray Weiss also shows every time, and the idea is that a pendulum is not in free fall. However, a pendulum has a resonant frequency, and which is given by the weight and the length of the pendulum and so on. So if you add an external force that is at much higher frequency than the pendulum itself, the pendulum doesn't feel it. Okay, so it's superposed onto the motion of the pendulum. Another way of saying it is that the swinging mass behaves as a freely falling mass at frequencies that are removed from the natural frequency of the pendulum. Does it make sense? Is that like that? So in the demonstration, but I don't have my badge. It involves. Let's see if I can break something. It involves doing the pendulum, and then you add a little. Okay, it doesn't work this way, but a little vibration on top of it. And with respect to that, effectively the pendulum is a freely falling mass. You still have huge problems with alignment and with keeping everything in lock. However, let's see if we can get the precision that we need, okay, in the measurement. So the signal that was seen in 2015 was of order 10 to the minus 21, 10 to the minus 22 strain. So that's the fractional oscillation of the length in the interferometer. So we need to get there. So you may say, let's make it long. On the Earth, it's hard to do things longer than 1 kilometer. Yes? Need a microphone, yes.
So, do you mean the mirrors in the experiment are on pendulum?
Yes, they're suspended, yes. Yeah. So that's it. Yeah. Filippo, you need the...
Can't you say that the mirrors are freely falling in this direction but not in this direction?
But they can't be freely falling in that direction at all frequencies because you need to keep them on the fringe. Mm-hmm. So you can't let them oscillate. In fact, you need to push on them a little because, for instance, the laser itself pushes on them and will tend to move them apart just from the pressure of the photons. So you do need to control them along all sensitive axes. But you do so, the control is at frequencies that are low, so like 1 second, 1 hertz, compared to the signal that you want to see. LISA is a little bit different. In LISA, the masses are actually freely falling, but only along one axis. And all the other axes and the rotational degrees of freedom are controlled. But there's one axis, the axis of where they're freely falling. In fact, Antoine can tell me if that's exactly right. But so it's only in like emergency situation that one would push on the sensitive axis, I assume. If but that's the difference with the Pathfinder, where you had to put a constant push on the masses because they were in the same spacecraft, and therefore you couldn't let them both freely fall. Okay, we're getting ahead of ourselves. I'm doing my order of magnitude stuff here. So how well can you do? Let's say on the Earth you can do better than 1 kilometer, maybe 4 kilometers, right? That's already very long. If you go longer than that, the light falls, okay, in the Earth gravitational field, which is annoying, okay, because and plus, you know, at some point you run into cars or people shooting at you at your experiment. Remember, it's in America, so it's animals. But if you do that, let's say we can resolve one fringe of the laser, one wavelength over the length. That's a micron over a kilometer. That's 10 to the minus 9. Okay, it's way far from what we need, which is 10 to the minus 21. Okay, so let's say we want to. Can we extend the effective length of the instrument? Good old Michelson and Morley did that. So their first version of Michelson interferometer wasn't sensitive enough. So what they did was they folded the light along the table. So if you multiply your mirrors, or maybe you can actually bounce the light back and forth, and that accumulates more signal, right? More phase delay and so on. At some point, the German interferometer called Geo 600 was doing that just twice. to back and forth, but it's hard to arrange. Now you have to worry about keeping two different spots with some angle between them and so on. So what's more feasible, or actually smarter, is to do a fabric-Perot cavity, where each of the arms is replaced with an optical cavity with a partially transmitted mirror at the entrance, so that light is trapped inside, and it does, say, 100 bounces, you know, back and forth. Okay, that gets us, actually, I think here we're saying 1,000 bounces even, gets us 10 to the minus 12. Still not enough. Well, what can we do? Can we do better than a fraction of a wavelength? Sure. We can try to do interferometry, can be very precise. So what limits you there is quantum physics. Okay, is the fact that basically when you measure, I'll show it more precisely later, but when you measure a distance using lasers, you're limited by the fact that your photons are discrete, effectively, and they come more or less like a Poisson process. So their time of emission and arrival is more or less independent from each other. So the statistics for Poisson, they go as the square root of the number of photons. That's your error, your natural fluctuation in the signal that you get. That means when you arrange for your interferometer to have a signal, a power signal proportional to the difference in the lengths, there's going to be a noise on top of that due to this shot discrete nature. And that's proportional. You reduce that by increasing laser power, and you gain proportionally to the square root of the laser power. So you do that. If we take 1 watt, which is already a decent red laser, you have 10 to the 16 photons. You do the math, and you're down in 10 to the minus 20. Okay, so closer, very good. And then you can do even more smarter stuff. You can say, okay, let's find a way to keep most of the power inside the interferometer. That's power recycling. Let's try to do a way to selectively have the signal resonate in the fabric-Perot cavity rather than the carrier, so the main part of the laser. And then after you've done all of that, you still have all the other noises, okay? Everything that's not quantum, everything that's related to do with the interferometer. So that means that these machines are extremely complicated, okay? Yes? Michael.
So your formula for number of photons tau is the time of the experiment, the duration of the experiment?
Yeah, so that's there I'm saying this is for 300 Hertz frequency, so I think it's multiplied by 1 over that. So roughly, more or less, the effective number of photons in this back on the envelope estimate is 1 over the measurement frequency. So it would, yeah. But then one can do it better, but that's... Okay, so I have a few slides that actually show the interferometry. We shouldn't probably try to follow the math too much, but the idea is that you can characterize mirrors by their reflectivity and transmissivity. These are complex numbers. They're actually real numbers for simple mirrors. And these are the things that you can tune. Okay, you can build mirrors by changing the coatings to have different reflectivities. The main thing is this is microscope interferometer. The simpler things you can model. At this level, you model each field just by a traveling phasor, a complex phase. You can track it along the interferometer. Interferometer splits it, so in amplitude it will give you 1 over square root of 2, and you see what's out here. So you see the ratio of the electric field at the photodiode at your measurement over the input electric field. And you can write it as something that's a function of the difference in length between the two arm lengths, this delta, half the difference. And so it turns out that if you arrange for everything to have no light when the two arms are equal, then when they change a little bit, you get a signal proportional to the cosine of the arm length difference, and that's the gravitational wave times the arm length. Okay, so in practice, this doesn't work so well, but it's the idealized case. So you do fabric-Perot, okay? So you complicate things, you can do the math of your fabric-Perot cavity. This is somewhat formal, but one way to understand it is that so light has a certain probability of entering. Actually, certain fraction of the light enters. and then the end mirror of the cavity is taken to be perfectly reflective, then it bounces back, and it has a certain probability of, or a certain fraction of it can go out. So you cannot track one bounce. Some photons will do one bounce, some photons will do two, and so on. That's what gives you this, the summation of that is this denominator here, which is like a geometric series, pretty much. So you can, all in all, you can dial the reflectivity, sorry, the transmissivity going that way, going out of the cavity, to build an arm cavity gain, which is the average number of times that light bounces back and forth inside the fabric Perot cavity. And that's of order, in initial LIGO, order 140. Okay, so there, that is for you an effective extension of the length of the interferometer by that factor. Then there are some complications with regard to how you write the output. You have to worry about resonance. If the wavelength of light is exactly a fraction the other way, if the length of the cavity is exactly a multiple of the wavelength of light, actually you get perfect reflectivity. You get nothing in there. You get a standing wave. It cancels itself completely. So you want to be a little off resonance and work off resonance where you have a linear response. Power recycling. So then the game after this works pretty well, amplifies the signal, is to add more power light, more light power. The way you do it is to add another fabric Perot cavity in front of the mirror. So now most of the light, remember, since we're almost dark here, we're almost canceling it out, tends to go out back towards the laser. Let's bring it back in by adding a reflective mirror here. So doing that, you can get another factor of, I don't know, 50. Okay, and you think you could almost bring this to infinity, right? Keep really lots of light sloshing in there. At the end, you're limited by the absorption in the masses, in the test mass. You have some, okay? Some of this light will go to power. But yet another factor that multiplies your sensitivity. So what is it then? So this is what I was saying, more or less, more formal. You look at what you arrange for your intensity at the output detector to be proportional to your signal, your strain, your difference in the arm length. The constant proportionality includes all these tricks that you do with the fabric Perot and the power recycling. You compare that with the shot noise, which is again intensity times the energy in a photon, and that's your strain equivalent noise. Now there are, as always, some complications. So remember, I will show you, these plots where at high frequency the sensitivity goes bad, and the reason for that is that fabric Perot extends the length of the interferometer, but at some point while you're doing that, the gravitational wave will change phase, okay, because it's a wave that you're getting. When you do that, the signal doesn't build up as well. Eventually you reach a frequency where the gravitational wave cancels itself out across the fabric Perot. That you see you lose, therefore, sensitivity going to high frequency because of that effect. And last, this is kind of fun, which is we're using lots of photons to decrease our shot noise and get a better measurement. However, the photons also hit the test masses, and therefore they disturb the test masses. So they're themselves a form of noise, which is called radiation pressure noise. So in fact, you can see usually write the two things together. It's called quantum sensor noise, and it has a term that decreases with power. So that would be this one, which is the shot noise term. The more power you bring in and more recycling and so on, the better you're doing in your statistics. But there's a term that actually increases with power, because you're hitting the test masses with randomly, or in random events, and therefore you make them shake, and now the masses are not freely falling anymore. So it turns out for if you pick a frequency, you can dial the laser amplification numbers to get the best possible sensitivity, and that's called the standard quantum limit. Okay, and it's a number. It's I copy it here. I2 F2 ml squared. So mass of the interferometer, length, effective length of interferometers, Planck's constant, and that's it. It doesn't have anything about the laser, the power, the optics, all those things. So this can be seen as a limit, fundamental limit on this scheme, on this interferometric scheme that that monitors the position of the test masses. And since you know this is a IPhT, there's actually a hand waving argument to show that it comes out of Heisenberg's uncertainty principle. So you may say that we are measuring something like you know, it's a double difference of the positions of the four masses. You can make a momentum conjugate to this. So this is actually going to be mq dot over 4. You need the 4 is needed so that you actually have p times q, sorry, commutator q is IH. These are, you know, these are some macroscopic degrees of freedom to some extent. They're the position of the entire test mass there, but you're measuring it quantistically with a quantum measurement and with photons. So you may say that this applies. So what do we get? So at a later, if you wait a little bit, you get that your masses move. We can write this in terms of the momentum, and then we can do the commutator for this, which turns out to be 4 pi over m. And then from this we can do dq prime Heisenberg uncertainty relation tau over m. And from that you pretty much, I guess, multiply by another tau for the arm length, and you're back to this formula. Yeah, so you do your error squared times the measurement time divided by length squared. Okay, that would be your strain equivalent noise, and that is that without a pi square because the hand waving argument. And I still remember, you know, you may not know that Filippo and I went to college to undergraduate together, and my worst exam was quantum physics because I couldn't demonstrate that. Okay, going from the uncertainty relation, and I looked it up yesterday. I guess I still can't. It's complicated. Yes. So you replace the tau with one of the frequency, right? Yeah, that's the idea. Pi comes from the fact that there should be... No, tau is 1 over frequency, right? It's not angular frequency. I don't know. I think the pi comes from the fact the measurement isn't really like that. But it's, for one thing, you're not measuring position directly. You're transducing position into power. So maybe that's it. Who knows? When you start hand wavy, you can continue. But however, you can do better than that, right? So this is a limit for this particular interferometric setup. For instance, if you did an interferometer that measures momentum instead of position, you'd be fine, and you could beat that limit. Or you could actually try to massage the quantum noise properties of your optical states to move more noise into momentum rather than position and so on. And that would also allow you to improve on that performance. Advanced LIGO sees that. Okay, it's basically it basically sees the standard quantum limit. And okay, and finally, signal recycling. This is the one that's most complicated, and I didn't even try to cover it well. But the idea is you add yet another resonant cavity, this time at the output of your detector going into the photodiode. And the idea is that not only you try to create a resonance, but you try to create a resonance that's frequency dependent. So that's what's shown there at the top. And then you have one parameter, which is the lag angle related again to the transmissivity and reflectivity of that mirror. And that lets you basically improve your low frequency sensitivity, or at the other end, your very high frequency sensitivity, or something in between. So you're not reducing noise in the integral, but you're kind of massaging it. You're crafting it to be at where you prefer. And so in general, you're better off with as much sensitivity as you want, but there are some cases, for instance, to follow neutron stars, where you may want to have a more peaked sensitivity that's really narrow banded there. At some point, I think there was even a concept where they said, okay, when we detect a signal that starts to enter the interferometer, then we're going to tune this dynamically to follow it across the frequency band. So that's too hard. Okay, I think when you adjust these parameters, then the interferometer needs to settle and so on. But the idea is you want to store your signal, which is a sideband, because it modulates the carrier power in the laser. You want to store it longer than the noise and the laser. And then, well, environmental noise, more and more formulas, but the world is not just quantum, I guess. So starting with thermal noise, of course, things at ambient temperature, they shake. So what you can do is, well, actually, let me start with this. Seismic noise, okay? Everything's shaking. Even the ground that we're on is shaking at the level of a fraction of a millimeter all the time, okay? At frequencies of 1 hertz, kind of slow, and below, even bigger, 1 hertz, 10 hertz. That turns out to be a huge limit, okay, for LIGO. And so what you do is you can attenuate it with pendula. Again, you suspend the test masses. Suspending the test mass gets you a mitigation of your noise by a factor that's proportional to the natural frequency of the pendulum. These are slow pendula; they're around 1 hertz, I think. Even this is not enough. So what you do is you chain the pendula. So in initial LIGO and Virgo, I think there are 5 stages of pendula, and some of them are actually inverted. So you can do a pendulum also by suspending a frame onto springs. Okay, so there are 5 stages of this on top of each other, and the test masses are finally hung on the final stage. So that's why there is the seismic noise has a frequency dependence of it's natural thing, but there's an f to the 10 in front of it. So it's extremely steep at low frequencies because of this attenuation. Thermal noise, everything shakes. In practice, some things matter more than the rest because you're coupled very selectively. So it turns out that mirrors vibrations are a big one, and I guess that's this one here. So that's just the fundamental mode, let's say, of the mirror. That's the one that couples the most to reflecting back the mirror. Violin modes are the fact that it's what was happening there. So that even when you have a pendulum, it's not a stick that goes like that. You can have modes of the string, let's say. But these are high Q, meaning they're very highly resonant, and they end up as noise in very peaked frequency in the spectrum. And finally, the one that's it's a bit surprising if you think about it. It's where the pendulum is suspended. So the fact that you need to have your wire into some kind of rigid hold, and there's a little bit of friction there. And in all this game, you use so who's statistical physics key enough here to recognize that that formula? So that's the fluctuation dissipation theorem. Okay, so it's the fact that in principle it's very complicated to figure out the fluctuations of the system, but you can actually compute them by just describing the response of the signal to linear solicitations, to linear input, and then it turns out that your thermal noise spectrum is just proportional to that. To those with a KT thrown in, because that's what makes thermal. And finally, and these are, fundamental environmental noise, gravity gradient. So the fact that in the atmosphere, on the ground, things move and shake a little bit. So you have perturbations in the density field of the atmosphere and the ground. Those create a time-dependent Coulomb potential, okay, just the Newtonian attraction on the test masses. Then locally we'll have a tidal component, therefore we look as gravitational waves. So no, seismic is actually shaking. So the Earth moves, the pendula move, and therefore they shake the mass. This is the fact that the ground moves, and its density is not constant, and that creates a time-dependent Newtonian force. Actually, another manifestation of gravity gradient is just a person walking by the test masses. So that's that you can't have, right? That's a time-dependent acceleration force toward the person. So there's a safety limit, which is not huge. It goes down as 1/r², but yes.
So you mean that LIGO is so precise that the gravitational field of a person walking by too close will disrupt it?
Yes. Yeah.
Okay.
Yeah, I think that's correct, and maybe there's some second order effect. Okay, when you walk, you push on the floor. That's seismic, let's call it, but that's also can also be gravity gradient. I think the dominant here is atmosphere and the ground. So the motion of the ground, actually that effect goes down as you go deep. So that's why the third generation detectors will be putting mines effectively underground. There are also some schemes to detect this. This you can detect to detect this actively. So to have sensors that there will be accelerometers basically near, and then if you detect that effect, and not the gravitational waves, just that you can try to subtract it. You're going to say something?
Yeah,
also?
I had just a curiosity.
Yeah.
What is the length of the suspension?
It's like 2 or 3 meters altogether. Okay. I think. Oh, here's one. So although these may be Virgo, I'm not sure. I mixed them up a little bit, but that's. Actually, no. I think this would be LIGO, because in initial LIGO there were 2 interferometers on top of each other in the Hanford Observatory. Not anymore. One of them is going to India. But that's and the technology for these suspensions was really developed with Virgo in the French-Italian experiment. There's something they call the super attenuator, which is really this. But otherwise, when you go see LIGO, it's not very impressive because it's all inside these big vacuum tanks. There are big tubes inside galleries. Masses are pretty, and so some of the interferometry is impressive. So this is more or less the current configuration. Now the input is not 1 watt, it's 100 watts. So this is enough that this burns. If you don't want to put your hand in it's a infrared laser, but power recycling factor is something like 40. The Fabry-Perot effective gain is 300. So the circulating power inside the arms is almost a megawatt. Okay, that's a lot. It's enough that you want the mirrors to be very, very perfect, because any imperfection will really catch that power, and it will either burn or it will create a hotspot and disrupt your interferometry. And then signal recycling mirror. So this is the idealized view. This is in practice what people reconstruct in terms of the spectrum. And most of these lines are not the things that I showed you. There are other sources of noise that are due to the readouts, that are due to the control system, which is the sensing that keeps track of all the degrees of freedom of the masses and keeps them aligned. I can't even read up there, but there's dark noise, which is some photons that go out that shouldn't. There's angular controls, attenuator noise, laser amplitude noise. The laser itself, although you do interferometry, has some fluctuation of its own. And this I showed last time. So this is what was achieved for the first detection, still a factor of a few away from design, but a good factor of 5, I guess. It's more like 3, better than initial LIGO, and this is what the future designs will try to achieve. ET and Cosmic Explorer are new designs that will require longer arms, underground possibly operation, cryogenic operation possibly, cool everything down to reduce thermal noise and so on. Voyager is the design that pushes the current LIGO infrastructure to the best that it can do. And it will be it is already a network with the 2 LIGOs and Virgo, Geo running on and off, but it's not very sensitive, but it is very sophisticated and does lots of prototyping. Kagra will actually join the 3 Western detectors. It's in Japan in the Kamioka mine, and it's planned to observe simultaneously with the other one starting in November, I think, the next observing run. But it's yet not sensitive. Although it's underground and cryogenic, it's maybe it's not as high power. And India is getting one of the LIGOs. Although I still think maybe they have broken ground for the actual installations, but it must be several years away. Okay, into space then. Any last question about LIGO? So, very complicated machine. It used to be that they made theoreticians and data analysts go there and be in the control room, which is, you know, screens and computers and so on, to give them an appreciation of the work of the experimentalists. But I did that, I think, 3 times, and it used to be shifts, 8-hour shifts. You could pick whether it was day, evening, or night. But I was totally useless, basically. So there was an operator who knew how to lock it and put it online, and then it would say, okay, scientist on duty, can we go into science mode? So, okay, if you say so, it was a science mode. And then you had a checklist of things, but they were like, write in the log what happened. And then if you see extra noise, do an investigation. But fine. So then you had this monitor. And so the system there is so complicated. It has 100,000 auxiliary channels. Although I think some of them are probably many small bands of the same one, but they're all things that are monitored. Seismometers, magnetometers, all this light pickups, light readouts, degrees of freedom, how much current goes into that actuation and so on. So it's all recorded, not as fast as maybe at 1 Hertz, okay? But it's a lot of data. So in principle, the investigation means try to see if any of those channels has excesses or has glitches or what happened or whatnot. And if you don't know what you're doing, basically, it's useless. So then after a while, they replaced that with a tax on the on the data analysts. So that funds proper experimentalists to do that work and to be basically the groups that are more all the groups fund together these fellowships that do the proper experimental jobs. But for a while, you know, we had to go there and pretend we were doing something and think, oh, the experimentalists are so great and so smart. So, which they are. I mean, 10 to the minus 21. So, okay, let's go into LISA quickly. So same idea, monitoring. Okay, what was I going to say? Oh yeah, oh, free fall. Okay, so that was the problem. To do the Pirani concept, we need to achieve free fall. On the ground, you do it with pendula, but you can't really do it below 1 hertz, below 10 hertz, a few hertz effective frequency, because things have to, you know, to stand still effectively. Okay, you can't have a pendulum on the Earth with a period of an hour or 2 hours. It just doesn't work with that. So you cannot get effective free fall at frequencies lower than 1 hertz on the ground. So you go into space. You go into space where what is now the effective frequency where things change? It's the frequency of celestial dynamics, is 1 over a year. It's okay, maybe Mercury, but still, it's everything is much slower. And if you just let masses fall there, you can be okay to think that over a time of an hour, 1 over millihertz, let's say, which is where you want to look for supermassive black holes, you're effectively falling freely. You can again use lasers to measure the relative distance of the spacecraft, and you can look at the oscillations in the distance that you measure to see gravitational waves. Actually, this is supposed to move. Yeah, see, it does. There's a very smart orbit that people figured out that if you put 3 spacecraft into orbits that are Earth-like, but they're tilted a little bit, then the constellation will form, will create a rotating triangle that's almost rigid, you know, with a period over a year. The deviation from rigidity and equilateral is something like 1%. So it's very good. Oh, there's this also. So let me go here first. So free fall, again, okay, we're in space, we're falling freely, but you have to measure. You have to put lasers around these things and so on. You have to put a spacecraft around these test masses. And spacecraft carry noise, they carry also acceleration because the sun is pushing on them. So the idea here is, again, selective free fall along the line of sight to the other spacecraft. Okay, so you're in that direction, that degrees of freedom, you're freely falling. Otherwise, the spacecraft follows sorry, not otherwise. Along that direction, the spacecraft follows the test mass. So if it's falling a little bit because of gravity and so on, the spacecraft pushes with cold gas thrusters to follow it. A cold gas thruster is the how to describe it? It's the simplest thruster you can think of. It uses just what is it? Newton's third law. Has gas in it under pressure. A little valve. You open the valve. You have gas going out. The momentum of the gas that leaves is matched by momentum in the spacecraft. So you're pushing. You're not burning anything. You don't have charge. It's purely a release of gas, neutral gas that way. So for that reason, if you don't need a lot of thrust, and in this case you don't want it, you want just a millionth of a Newton. Okay, so that's a good choice. And if you see all these CubeSats, you know, there's very small satellites that are launched for cheap and little power and so on. They tend to, if they have thrusters, they tend to have cold gas thrusters because they're simple, just a valve. You want to make it as long as possible. In the current LISA plan is for 2.5 million kilometers. You never do maneuvers, and that means that celestial dynamics is going to be quiet. However, 2.5 million kilometers. You have a laser, you point it at the other spacecraft. If you can find it, in fact, it's a complicated process even to acquire the signal from the distant spacecraft. It's very far, it's a small dot out there. You only get something like 100 picowatts at your through your telescope, which is 30 centimeters, still accurate. So you get very little power, so there's no way you can reflect it back and do either Fabry-Perot or even a Michelson interferometer. So what you do is you measure it with a local photodetector, and you phase lock the outgoing laser to the incoming one. So you kind of create a mirror with electronics. That's one way of thinking about it. But that means you have the noise that of that measurement. So it's useful to think of LISA as this one-way measurement that you combine to realize an interferometer. You still need the interferometry as you did in LIGO because you want to cancel out the noise from the laser itself. So its own fluctuations that otherwise would look like, again, gravitational waves. And then the sources of noise. This is a little bit different than I was showing because these are not fundamental derivations of the level of noise in LISA. These are actually the requirements that are put on the mission to achieve its scientific job. But basically, you have shot noise and other optical noises on the high frequency end of LISA. You have thermal noise, residual stray accelerations in the test masses, some due to the fact there's some gas around, some of it is transmitted by the spacecraft at low frequencies. And in frequency, if you plot in terms of the gravitational wave observables, shot noise, optical noise is blue, so it increases with frequency. Thermal noise is red, because it's an acceleration noise, but you care about distance, so you have to integrate twice. When you integrate, you divide by frequency, right? That's more or less a general rule of thumb. And also, as with LIGO, if your frequency gets high, above a few tens of millihertz, you're going to have a different wavefront that hits the two spacecraft, the three spacecraft into interferometer. So you're going to lose some of the signal because you're not because you're sensing different points in the wavefront themselves. So that also reduces sensitivity at the high end. So this is the result that you get. This oscillation here is due to this effect of the waves not building up fully coherently because of their wavelength, which is smaller than the LISA arm length. They're not that deep because this curve is integrated over all sky positions, and therefore, on the average, the effect is different, right? Because the wavefront, the delay is wave number times the vector between the two along the arm, and it shows the classic sources for LISA, which are the supermassive black holes. Although I showed you that the amplitude of the signal increases with the frequency, if you see it in the frequency domain, it actually goes down because it spends less time at the higher frequencies. But this is the classic shape that one sees. These dots are sources that are in the galaxy. They're binaries of white dwarfs and neutron stars. These are almost monochromatic and will be seen as lines effectively. These are the extreme acceleration spiral. I'm going to talk about them maybe next week or the week after that. Small black hole falling into a big one. Lots of orbits. It's not a finite spiral because since the mass is very small, it loses much less energy to gravitational waves. And there's one source I don't show here, which are the LIGO Virgo binaries that would actually start their life. They would actually not. They start the life at very small frequencies, but they would spend a few years in the LISA band before getting to LIGO. And then, what do I have next? Oh, okay. So this movie, the actual structure of LISA keeps changing as different industries do prototypes and so on. So this is a few years old, but basically the spacecraft is built around two telescopes that are pointed along the sides of the triangle. It's a little slow, but this was a German animation with very hard rock music, basically metal almost. So it was so telescopes. They gather as much of the signal they can, and they funnel it or focus it into a local optical bench, which needs to be as rigid as possible. Let me finish while it goes. On the optical bench, there are actually two different measurements that one does. There's a measurement of the incoming signal with respect to the optical bench, so the spacecraft itself, and there's a measurement of the spacecraft with respect to the test mass. which is a precious metal cube, you know, very, very resonant, high Q and all that, suspended inside a cavity housing and monitored so that you can actuate those little things where they're cold gas thrusters, so that you can actuate and move the spacecraft around the test mass on the sensitive axis. Okay.
It was a question on the previous slide.
Okay, let's see if I can get that.
The verification part.
Oh yeah, so these are galactic binaries that are so the question is what are the red dots here, and there should be more than these 9. So these are white dwarf binary systems in the galaxy that are known from optical observations. So there are very nice experiments that actually see them, and they can track their I'll show it in next week or the next. They can build a light curve for their emission. Some of them are actually eclipsing. So with respect to us, you have one of the white dwarfs passing in front of the other one. In that case, you get a very nice signal in the light curve that that describes the eclipse, and from that you can even you can measure their masses, or you know their frequency effectively. You know the orbital frequencies. So these are sources that are known to be there. Their distances are known to a few tenths of percent. So the ones plotted here are verification, because we know they're there. As soon as we turn on LISA and wait, you know, 3 months or a year, depending on which one it is, there will be a signal from that system. All the other ones are binaries that are expected to be in the galaxy because of our models of stellar evolution and so on. So these are just put here randomly according to some theoretical distribution. Those will also be seen by LISA, but we don't know where they are or what frequency they are. So that's that's the idea of verification binaries. Some even say that the verification binary can calibrate the emission, but I don't think that's right, because for most of them we don't have a good enough distance that I think there's even a couple of these where one can see a decrease in the orbital evolution due to gravitational wave emission. 1 or 2. So these are seen now. These are monitored using this time domain astronomy experiments, right? That take like ZTF in the US. There's I forget the main European one, but I think there's one that the Netherlands has, where you take repeated pictures of the same patch of sky over 1 hour, 2 hours, in the course of the same night over multiple days. So you build up many points, and you see effectively the light curve, the time-dependent light curve from yes.
Okay, so in principle, you should be able to see the superposition of all these verification signals and being able also to disentangle them, or
yeah, I mean that's a big deal, right? So if you go towards the high frequency end, they're actually distance enough that back of the envelope you can say each of them has enough measurements, enough frequency being wide enough that you can do it individually. As you get to lower frequencies, you have that some louder ones actually hide the weaker ones. So if they're comparable, a little bit overlapped, you can resolve them together by fitting them together. As you go down in amplitude, eventually you'll have a large population of these. Most of the 10 million or 20 million that is unresolvable, and that gives you a stochastic signal. So in the original LISA, that stochastic signal was actually a source of noise. It was above the instrumental noise. Now it's comparable, I think. It depends which kind of galaxy model you take. But that's one of the data analysis problems that one has to solve. And there are some demonstrations that if you simulate, say, 10 million of these binaries, you can resolve something like 10,000. I think. What did Tyson did? Did he get to 10,000, 5,000? 20,000. He got 20,000. 15. Okay. So you don't actually search. You search for them in bands. You try to harmonize the bands and so on. It's not complicated. It's complicated in practice more than in principle. The idea is that it's a joint fit for the parameters of all those sources that are mostly orthogonal because they are different frequencies and almost monochromatic. So Okay. Oh, here I had the LIGO binaries. They just needed to appear. Okay, and then yeah, let me do this for 2 minutes. Time delay interferometry is the idea that okay, so in a microscope interferometer works. Do I click on this? How does? Let's go. It works because you have the same phase delay along the two arms, and therefore, if that little ball represents a small error signal, so a small fluctuation in the laser frequency, once it's back, it cancels out. So interferometer cancels the common mode, it's called, so the signal that you have along both. It detects the differential mode, so the gravitational wave, which would shorten one arm and lengthen the other one. However, what happens in LISA is that the arms cannot be equal. So show me this one, please. The arms cannot be equal because of orbital dynamics, okay? And so now you don't cancel out your error noise, your little laser noise fluctuation, and you're left with a lot of laser noise actually because of this. So if you don't correct for the effect, that would be 10 to the 8 times stronger in amplitude than the signal that you want to see. Because effectively you're not doing interferometry. It would be doing like a microsome with grossly mismatched arms. You cannot cancel out the fringes because light is not coherent over the time. So then the inspiration, the idea was originally, I think, Armstrong, Tinto, and Estabrook, was then to basically, show me this one. Okay, I have to click 3 times to do a double bounce. Okay, so effectively let light go along one arm and then the other, and then combine that with light that goes along the other arm and then that one. If you do that for static spacecraft, at least, you again build up the same phase delay, and therefore you cancel out laser noise. And you can do lots of little tricks with this. And so, for instance, if the spacecraft are now moving, again you lose, because when you do this, you still, if the spacecraft are moving, you're still going to get a different delay along the 2 paths. You do it again. Okay, so doing that, luckily, it doesn't affect your signal so much because it differentiates the signal, but also the noise. So you keep the same sensitivity, but you reduce this laser noise that otherwise kills you. So I've written lots of papers on this thing, so I like it. And Antoine too. In practice, of course, it's much, there are complications, time synchronization, sidebands, and finally, I think this is the, oh, look, didn't know I had that animation. So Pathfinder was an experiment to test out the LISA test masses, so basically the free fall along one axis. You know, APC and Antoine had a big involvement in it. It launched in 2016, I guess. 15, operated in 16, 17. So it recreated one of the large LISA arms, shrunk into a single spacecraft, with one difference that we mentioned before, that actually you have to push on one of the masses to keep them the same distance. But the idea was to see that you can follow them using your thrusters and reproduce very low, reduce acceleration noise. And actually, it was quite striking that it massively overshot its requirements for success, which I suppose were conservative, but still it actually did better than, it behaved that the LISA requirement or better. So if you took exactly, to some extent, the LISA Pathfinder system and put it on LISA, or at least achieve the same performance, then you'll be fine. You don't need to demonstrate an improvement in terms of acceleration noise. This is a plot of acceleration noise as a function of frequency in what is this? It's an acceleration of a square root hertz. So it's an amplitude spectrum. And yes. Okay, so we're moving on to pulsar timing, but maybe we can do our coffee break, Ricardo, if
Whenever you want. Now.
Yeah, we are at half time, so and I'll be quicker on the second part. We let the pulsar go while we. Welcome back. I hope you're caffeinated, and we're going to. We have 40 minutes, so I'll go a bit fast about pulsar timing, since we're going to pick it up again when we do parameter estimation and discuss data analysis, and because I guess it sounds like also I may be giving a seminar about this at IAP sometime in June, about the latest results. The idea here, remember, gravitational waves you get with the propagation of time of exact clocks. If we want very long distances where we cannot put a clock out in the galaxies, but we have pulsars discovered, what, in 1957, and especially millisecond pulsars. These are neutron stars that are rotating very rapidly, and by a lighthouse effect, so they're emitting radio beams along its poles, but the axis of emission is displaced with respect to the axis of rotation, so they behave like a lighthouse if we are in the right position with respect to Earth. And so what this does is to give you repeated pulses with periods that can be as small as milliseconds. So maybe 100 milliseconds or 50 milliseconds. And from this, you get a very, very interesting data analysis with lots of details that works surprisingly well. So what happens is that individual pulses are actually don't look very regular, because while the rotation of the pulsar is very regular, there's a stochastic emission process that's superposed on top of that. But once you average hundreds of thousands of these pulses, you get a very stable profile. Okay, so this profile depends from the geometry of the rotating system, whereas the individual pulses depend from more stochastic effects. What you can do with this profile then is to compare it with a model, with a template of the profile, and determine its position. So then these average pulses are very, very predictable. Okay, so over years, you can build a model that predicts when they will come to within fractions of a microsecond, 10, 100 nanoseconds. Model is very complicated. There are lots of terms here. So the time of arrival of the pulses, this time of observatory, can be turned into the time of emission at the pulsar by subtracting all these effects. So for instance, you want to, you want to correct your observatory clock to a universal clock, universal time coordinate, UTC. We have to subtract effects from the troposphere, so diffraction in the atmosphere of these pulsars. A huge one is the Romer delay due to the motion of the Earth in the solar system. Okay, so that's big. That's 500 seconds, right? Over 10, 100 nanoseconds. We're going around the sun. There's a Shapiro delay that you can see from the sun. Okay, so and the other planets. In fact, you can see Jupiter and Saturn in the Shapiro delay. Dispersion measure is the effect of the columns of free electrons in the interstellar space between us and the pulsar, which are changing over time, and which create a frequency-dependent delay. You have effects in the binary itself, Romer delay in the binary. All of these things have deterministic effects in these times of arrival. After you've taken out all of them, you're left with a model of the evolution of the pulses in the pulsar itself, whether it's slowing down, whether it's fluctuating, and so on. And what's left after taking out all of that and fitting all of that is the residual, which is our data, and we should be zero except for gravitational waves, right, that affect the propagation of the signal to us. And this is a plot of the Hals-Taylor pulsar, okay, so discovered in '73, where they were able to monitor the period of the binary, and they saw, using this technique, just seeing all these pulses, you'd measure it every month or every week and so on, and fit all these parameters and look at the evolution and see that it matches the general relativity prediction very well. Or rather, the quadruple formula, okay? If you have another theory that does quadruple formula, it works equally well, but it turns out in '93 there were lots of theories of gravity that did not either have gravitational waves or that had different prediction, and so that was the biggest death cut on gravitational theories. The second one was after GW170817, where it killed a good swath of Vernizzi, Langlois. Who are the other names? Your theories of gravity. There are a few names attached to it. We should say it. This is how the data set look like. Each of these points is one of these observations of residual. These are, for instance, in the NanoGrav, the US collaboration, all the pulsars that we've been monitoring, showing different things here, and we'll go in more details next time. But there's also here international efforts to monitor pulsars. And the idea is the signal, we saw this response already, the signal is an integral of gravitational waves along the line of propagation. This is a tensor dotted into this piece would be the vectors to the pulsars. So you don't want to do this with a single pulsar, because there's one thing that you don't control, which is the evolution of the spin itself of the pulsar. If that had, for some reason, some low frequency, slow evolution, it would look like a gravitational wave again. So what you do is you monitor lots of pulsars. This idea goes back to Becker, Wahlquist, and Hellings, and you try to look for the same effect, or rather for a compatible effect given the different geometry in all of them. So there are three big collaborations that are doing this across the world. And the US was using two big telescopes, Green Bank and Arecibo, that you may have seen crashed spectacularly in later last week. So it's not there anymore. Pulsar noise, lots of sources here. This is the equivalent of shot noise, radiometer noise, how well you can see these weak signals from the pulsar, and a Gaussian, basically white noise effect. But you have other things due to the fact that the pulse realizations don't quite average perfectly. That timing noise would be that the spin is evolving. dm is this distance, this effect of electrons out to the pulsar. This is chromatic noise would be other diffraction, scintillation effects in this refracting medium. This is from us. Errors in our clock that we use to refer our measurements, and errors in our knowledge of the Earth's position around the very center of the solar system. And finally, after all this, you should have a gravitational wave background. This is an equivalent sensitivity curve. You see it's much worse than what LIGO has, but luckily black holes are very big at this, the black holes that are orbiting with frequencies of 10 to -8, 10 to -9 hertz. So there's this quasi detection, or first step towards the detection, that does see a big steep signal. This is frequency, this is the residuals that you see, which would be compatible with, this is seen in multiple pulsars in the array. This would be compatible with a stochastic background of many black hole binaries at the centers of galaxies, none of them strong enough to be seen independently, but all on top of each other. We do hope, and I'll tell you more in one of the next episodes, we do hope that the next data set will have enough strength to show that the geometric relation of the signals that we get is coherent. So you're not just seeing, each pulsar is not just seeing noise from gravitational waves of the same amplitude and spectrum, but they're also seeing the same realization of noise, okay, with the same geometric thing. So that's a weaker effect, and it will take more work to see it. Okay, and with that, we're back to theory. So we can, half an hour theory. How's that? So last time, we introduced gravitational wave emission from binaries with dimensional arguments back of the envelope. We got it right, except for the coefficients. Okay, so to get that, unfortunately, you have to do equations. We do know that, we do know that the linearized metric perturbation, RH, satisfies a wave equation. If we go to the best gauge, it looks very clean. It's a square of H equals, what is it, 16 pi, the matter tensor. And in fact, there was a question last time if one could do, remember I showed an equivalent formula for Riemann, and showed that Riemann also can do a square. the question was whether you can put matter there as a source for Riemann, and you can't actually. So to get that clean shape, you need to use Einstein's equation in vacuum, and so you cannot use the Riemann formalism to do emission. You need to work with the metric. And there's also a justification in terms of the degrees of freedom if you do that, because Riemann done that way with the symmetries ends up having only 2 degrees of freedom, but to couple with matter you need more, right? You need the quadruple, which has 6. So you need to work with the metric and not Riemann alone. So I'm going to show you that if you do Green's function on this linearized metric perturbation, you get the quadruple formula, but it's a strange halfway theory that gives you the emission, but it doesn't allow for gravity, for one thing, for the system itself to be orbiting, and also it doesn't allow for the loss of energy to this for the system. So you have to go to actually second order theory, and that let you identify a gravitational wave momentum tensor, and also they let you have gravity, which means you can't use the naive quadruple formula, but you have to do something more sophisticated, which is matching, that's fine, asymptotic expansions of the local geometry, the local dynamics of the binary with the distant propagation of the waves. And these matched asymptotic expansions, we'll see them in more detail either next week or the week after that when we talk about post-Newtonian and EFT methods to compute gravitational waves. But they're the basis of it, basically. You have 2 different regimes of lengths, and you need to match them. Okay, so the naive formula. This is what we saw last time, trace reversed perturbation of the gravitational wave field. It leads to a wave equation in the Lorentz gauge. This you can solve with a retarded Green's function. You know, everything is weak, so it looks like flat space. Looks like a linear spin-2 theory on flat space. Now, from a retarded Green's function, you can do from these expressions by approximating the distance between u, okay, where you measure the wave, and the point masses in the binaries or the distribution of matter. By approximating that as just one distance, you get effectively the multiple expansion. Okay, and to make it clean, you actually so here everything is moving slowly locally. It's a non-self-gravitating system, so it's not a binary. It could be me moving my hands, or it could be a mass on a spring. If you know, you need a big spring to get something decent. But so everything is moving slowly. We can neglect everything except for the mass energy components. However, again, from this is now. The divergence of this expression is 0 just by symmetry and by the equation of motion. So that means that there's a conservation equation for the energy tensor momentum, which is what actually doesn't let you have any gravity. This matter is just moving freely in space and conserving momentum. But from this conservation of momentum, you can derive the tensor Virial theorem, which I spent like 2 hours on this the other day, because usually the textbooks say, okay, now we're going to use the conservation equation. You combine equations, you take some divergences, and then you can relate this T00 to the second derivative of Tij, so of the stress. Fine, but what does it mean? Okay, it turns out it's one manifestation of the tensor Virial theorem, which relates stress to the second derivative of the moment of inertia in a binary. And if you then go look in the textbooks of galaxy structure and so on, it actually does a lot more with the tensor Virial theorem. There are more terms that involve the flux of energy and so on, and it's quite meaningful. But at this level, there are only 2 terms, and it's what lets you then use. Now this Ij is this effectively, so it's the. You're right. I should define this. In here, yeah. Okay, it's the integral of this guy. So yeah, I should have that. and this is the quadruple formula. You get real physical gravitational waves once you project everything to the TT gauge. The idea is that you have only transverse degrees of freedom along the direction of propagation of the wave. You can always do that without changing the physics. Okay, and so this also removes the trace from the moment of inertia, and that's the classic. Now I said this is incomplete because it doesn't allow for self-gravitating systems, which is a problem. So this is then how you can look at things a little more generally. Now we're looking at weakly gravitating systems. Weakly gravitating systems means that gravitation is weak enough that the potential energy is not itself a big source of gravitational waves. So it doesn't really include, if you wish, black holes. Okay, we have to pretend that black holes are proper point masses to do this. Neutron stars are strongly gravitating, but only to the 10% level, so maybe that's okay. So the idea is what? You can divide space ideally in various zones. There's a strong field region where you're close to the masses and you see general relativity. It's complicated, you don't want to be there. If you go far enough, if you go, say, 10 total masses in terms of distance from it, you're in a weak field near zone. So I'm losing my laser pointer here. Do you have another one, Ricardo? Okay, it's come back. But so you can go far enough that a Newtonian description of the metric is accurate. Okay, for weakly gravitating system. And then Newtonian, if you remember your GR, the Newtonian limit of GR, you have the Newtonian potential in the time component in a quasi-flat metric. The first contribution will be the Coulomb potential, Newton's potential, but then there's a quadruple effect. You can just you can basically do a multiple expansion of the field using the same mathematics that you use for basic EM or for basic Newtonian field. And so you don't, in the center of mass frame, you don't have the term in 1 over r squared because that would involve the dipole momentum, the momentum basically of the distribution. No, sorry, it would involve the center of mass. It would be proportional to the location of the center of mass. Okay, so you have this. If you go out, local wave zone, now you go out to longer than 1 wavelength of light, so c over the typical frequency of the of the emission of your periodicity in the system. Well, here you're going to have a description that you have to have a solution that solves that. Okay, solves the wave equation, therefore looks like a wave. We know waves look like functions of t minus r divided by r. Okay, all of these would be solutions of the spherical wave equation, and you can build an ansatz. You can reason that if you have also to obey the Lorentz gauge and to solve this, your metric, trace reverse metric, will have this form, where you have in the time component you have 2 space derivatives. You trade one of them with a time derivative in the vector 0 time space components and with 2 times derivatives in the other. So if you plug this into the divergence, you get that not only every component is a solution of the wave equation, but also it all fits together. Okay, with the in the gauge that we gave ourselves. And now we match at the boundary, notional boundary between this weak field and local wave zone, we match this solution to this one. Okay, everything is moving slowly, so we can just disregard the time derivatives and only look at the 0, component. And these 2 derivatives space bring out something that looks like a quadruple component. And so effectively then you can match h00, this component, to that term up there with a 3. I have a different form for the I, but it's the same thing really. And so the part that I care about for the gravitational wave, which is the TT space part, is the second derivative of the quadruple moment over r, time the appropriately delayed and cast into the TT shape. Okay, so then that means that the naive formula was actually correct, okay, for weakly gravitating system. If you have a strongly gravitating system, okay, where it's not just really masses that are moving anymore. There's significant gravity and so on that affects the potential here. Then you have to write your potential out here and extract the metric directly by matching with the same principle. So you will not get that because it's not just matter, but you can use the same principle to do that. And that's what PN does. And in PN, you'd be matching to the post-Newtonian corrections to the Newtonian potential, really. And in EFT, you do a matching to this effective momenta multiples of the binary system, and you get the same thing. So here, things looks quasi-Newtonian. You know, velocities are small, and you don't care about time. You don't care about time derivatives very much. Things are moving slowly. Here, instead, it's if you want, this could be a Minkowskian or post-Minkowskian expansion, and you do need to keep actually the space and time derivatives have the same magnitude because that's what waves do. You know, for a wave moving dx or weighting dx over c is the same thing. Okay, so all of this is backed by very complicated papers by Damour and Blanchet in the 1980s. Some of them are even in French, so obscure they are. But everybody cites them and believes them. And the EFT approach actually cuts on all of this and very nicely. Maybe it involves more faith, but do you have something to add, Filippo? Or, because I think you've worked on. Did you have to do this for the scalar tensor, or does it come into the matching of gravitational waves, or you're doing? Yeah, yeah. Okay, so then I promised to talk about gravitational wave energy momentum tensor. What's the problem? For the linearized weak field theory, we can't really define a gravitational wave energy momentum tensor because of, again, the gauge freedom and the freedom to put yourself a free fall. So the theory is not consistent in a way, although we're detecting with these waves and we're saying that they transfer energy, and we see that the binary shrinks because it loses energy. We cannot define the quantity that carries the energy that's escaping. So one way, I don't know, maybe the leading way to define it is to talk now about perturbations of a curved space-time. You want the space-time not to just be Minkowski, but you want it to be able to be curved because that's what energy does. Okay, that's what the stress energy of the gravitational waves does. So you want to see that effect to define it. And so you define it as a background term with waves on top of it. And you talk about two length scales. The background is going to have you know, radius of curvature and variation in the radius curvature that are very large compared to the wavelength of the waves. So when you do that, then if you take a local average, kind of smooth out locally the value of the metric, you isolate the background. So you can then write your metric as a background metric, which is just the local spatial and time average, I guess, of the metric plus a perturbation. Same story, since Riemann is a linear function of G, same story for Riemann. Now we can expand the Einstein tensor, so what is it, Riemann minus 1/2 G Ricci, into a background term with only this RB, GB, a term that's linear in the gravitational wave perturbation, a term that's quadratic, and so on. And we now can set them to 0 individually, okay, to solve Einstein equations. So this one just tells you that the background space-time holds up as a, actually no, wait, let's look at this one first. So the terms that's linear in H gives you, through this, the wave equation for the metric perturbation in the curved background. Okay, since here we're not using the Lorentz metric to raise and lower indices and to take a covariant derivative, we're using the background metric, and that's what this bar here means. So what you get is, as a nice result of doing this, is that you can see how waves propagate in the curved background, and they propagate identically to EM, basically geometrical optics. Okay, they have They have gravitational wave deflection around masses. You get Einstein amplification around lenses. All that quite clean. Then the other two pieces, background plus the average of the second order, have to be 0 together. This averaging is non-local. And if you just take this second order term in Einstein and put it on the other side of the equation, you see that it behaves effectively as a source for curvature, okay, for the background curvature. So the degrees of freedom of the gravitational waves can be seen to curve space-time, and that's just in general relativity, the definition of energy tensor momentum. It's real energy. If it curves space-time, it must be real energy, real momentum. Let's just, if you just put together the formulas with Riemann, Ricci, it comes out as you know, a first derivative squared of the trace reverse perturbation. You can write it also in terms of the TT gauge expression, and it's very clean. Okay, so usual gauge, Lorentz gauge, and so on. This is very clean, and it's good to finally, if you describe your wave as the two polarizations, right, plus and cross in a certain direction, average over a few wavelengths again, I guess here, you get the energy carried by a plane wave per area, and it's proportional to a first derivative of the gravitational wave field. So in frequency domain, it's you multiply by f and square it. And now for a typical binary that we detect on Earth with the h of 10 to the minus 21 at 1 kilohertz, okay, maybe it's a bit less, the constant in front of this amplitude is actually rather big, right? So 0.3 watts per meter squared. I think the comparison was to the moon. Sun would be 1,000 watts, right, during the day. The moon may be a fraction of a watt, a full moon. So you could read by this if it was light. It's not, and the space-time is fantastically rigid with respect to these perturbations. So you know, you have to do quite some work with LIGO to see it. Which whatever it is, this can be flat space-time for instance, locally it can always be flat, but for instance, what propagation in the curved background is what gives you the redshift, the cosmological redshifts for gravitational waves. So you can use it that way. But here, as long as you average out the value of the gravitational wave over a few wavelengths, you're fine, basically. Okay. Emission from a binary. So we have our quadruple formula now. It's fully justified by by theory. One can work it out. You know, just 2-point masses. Simplify it at a distance. There's a reduced mass. Where is it? Somewhere. They rotate with a certain frequency. You build the quadruple tensor, or maybe this is just the moment of inertia actually done this way. Then you take a second derivative, you project it to TT gauge, and you get this classic form for the gravitational waves, where there's a velocity squared. It's the simplest way. This is the distance to you. In a cosmological context, it would be luminosity distance. The constant proportionality here is the reduced mass. So actually, it's one can try to match this theta is the angle to the observer. So if theta is 0, you're kind of looking up. You have the binary in x, y, and LIGO is somewhere up there along. And you can reason why these things go like that. So if that's the case, you would have the maximum effect, because you can't. The directions are what they are, right? So x and y is going to create quadruple moment along x and y. So if you're on top of it, you see all of it in terms of the transverse degrees of freedom. If you're edgewise instead, you would have at theta of 90, you'd only see motion along one axis, and therefore you'd only see one polarization really. And the other one goes to 0. And then we did this a little bit already, but principle of adiabatic in spiral is you can, with some effort, build an effective force out of the emission of the energy, of the stress energy tensor to gravitational waves. That's also averaged in some sense. So it's easier if the binary is proceeding slowly, so losing energy slowly enough that you can think of it as an instantaneously circular or elliptic binary that is slowly shrinking. It's easier to work at the level of energy, or conservation of energy. So energy of the binary, derivative of that will be minus the luminosity. There's yet another way you can write it for simple binary in terms of velocity. This leads you to an evolution of the velocity that shows you that actually the spiral accelerates. So the higher the velocity, the higher its derivative also. And then there are many ways to write it. And I showed you last week that you can write everything in terms of this chirp mass, which is a combination. I don't have it on this slide, but it's a combination of the reduced mass and the total mass, reduced to the 3/5 times total mass to the 2/5. Those exponents come from Kepler's law, which here enters to the frequency of the spiral, but also the radius and the orbital radius of the spiral. So you can plot the evolution of the gravitational wave frequency. It's something like a bit less than the 4th power, and you can write everything in terms of chirp mass. But you can also bring out the mass, total mass, and the mass ratio. This symmetric mass ratio is the one that gravitational wave people like. That also I should have put here, but it's basically the symmetric combination of the two masses, and it's dimensionless. This is equals 1/4 for an equal mass binary. It goes to 0 for a very unequal mass binary, for test particle really. So if you write it, if you bring out the masses that way, you can show that everything scales. If in geometrized unit you express time and frequency in units of the mass, then this evolution is universal. Basically, it depends only on this mass ratio. So that means that if you compute the waveform for any equal mass binary, you can rescale it to the waveform for a different one just by changing the time axis, which makes sense because if you see this, that's the only scale you have, the total mass of the binary, and I guess the mass ratio. That's the only thing that sets a scale, and therefore it makes sense that everything should rescale. Time to coalescence, just integrate this to infinity. Now, this is a Newtonian spiral where we're only using Newtonian energy and not higher corrections from general relativity and for the linear nature of gravity. So it will be more complicated than that. But still, you can see again that the binary spends most of its time at lower frequencies when it's farther apart, and very little at the end. It's a chirp that accelerated toward the end. The more generic formalism for adiabatic in spiral uses, typically one parameterizes everything with the velocity, as here, and then you write corrections to you write more generic expressions for the luminosity or for the energy. And again, you use an equation to relate now the phase rather than the velocity, but same thing, the orbital phase, to the change in energy. And you can plug this into the waveform that we derived last time, which is also a leading order waveform to get the main effect. And so that's where post-Newtonian theory comes. Okay, so this function for energy, luminosity, and phasing you can develop as perturbations on top of Newtonian theory. The perturbation parameter is the velocity squared, and it's how you count these post-Newtonian orders. So if we take just the first term, that would be the simple energy that we saw before. This also is normalized by the total mass. So this would be my 1/2 mass, reduced mass times v squared. And then you have corrections that come in as expansions in v squared and expansions in the mass difference, in the mass ratio between the two masses. Flux is more complicated. This would be accurate, I think, the way I wrote it, to 3.5, so to v to the 7 for the flux, and to v to the 6 for the energy. It's now known to 4 pn, right, completely. This is one way. So there are different ways you can solve that equation, that adiabatic equation for the phase. I forget which one this is. But in practice, these expressions, you plug that into the waveforms we saw below, and that is your accurate waveform. And let's see. Okay, so I can finish with this slide probably. Just to tell you a little bit, typical signal then looks like a long in spiral, where this thing I showed you is actually correct. And the branch of physics, mathematics, and of society that computes this is post-Newtonian theory, and most recently an RGR. So same calculations, but from a field theory and Feynman diagram approach. Many years of human years spent to develop equations like this. There are complications. Things get more fun if the binary is not circular. If it's eccentric, you get more interesting dynamics. And if you have spins at 3 degrees of freedom for each component. If they're black holes, that's all there is, right? There's a mass and a spin vector for each component. If it's a neutron star, maybe you can have some excitations also in the structure of the binary. Anyway, lots of physics here to get very precise shapes. In the first LIGO detection needed to model only 8 cycles. For neutron stars, it is more of an order of 100. I think that were seen because they go to higher frequencies. Okay, at the end of the spiral, eventually this V is too big to justify this as a perturbative expansion. It's also not adiabatic anymore, so the actual nonlinear dynamics of gravity of the binaries is too fast to follow using just the loss of energy. So really you shift to doing numerical relativity, to modeling the Einstein equations on a computer as a grid of many points. Again, lots of human years going into this. I may show something. For the nice educated black holes, actually the result is a bit underwhelming. Because the merger is very fast and it barely does it doesn't do anything weird. In fact, it resembles very closely the waveform of a test mass particle falling into a black hole, which was also. And then at the end, another field of society and physicists, you get a single black hole, the two black holes merge. The final mass of the black holes is the sum of the two. If it's 2 neutron stars, you may either form a black hole if you're above the Schwarzschild limit, or you may form another neutron star or some kind of metastable star that eventually also collapses to a black hole. But if it's a black hole, as we saw in the first LIGO signal, it will be an excited black hole, right? Not one in its quiescent stationary state. So you can do perturbation theory. You can look at the excitation modes, really the oscillation modes of the black hole, which are quasi-normal because they die out very rapidly, basically. And so you should see a signal at some fundamental frequencies that dies down quickly. And those frequencies encode the parameters of the final black hole, its mass and its spin. Okay, I think, yes, that's it. I'll go more in my data analysis discussion about which parameters of the system you can detect, measure, which are more important, and so on. But for the moment, we go through the theory for today. Good. 1 minute to go. Questions online?
Yeah.
Yes.
People online may ask questions by connecting with the microphone, and we will hear here. And of course, in the room.
So have we detected, or will we detect the ring down phase?
The ring down.
Yeah, because you say it dies very quickly. So
Yes.
do we get competitive constraints from this stage?
Kind of. I mean, they're let's see. Yeah, I think at least in a couple of black holes, there's enough signal in those that you can see at least the fundamental frequency, the fundamental quasi-normal mode. Not in the first detection. The first detection, if you remember the waveform, it was unclear. So I'll look it up. I'll see how many have an independent ring down detection. I think that's correct. This will be interesting eventually when even better detectors, and you see them very loud, and also in LISA for some systems where you can see that part very well, because it's a direct probe of the black hole structure as a black hole and not as something else, or even of theories of gravity, that different theories of gravity that may give different quasi-normal modes. So it's the people talk about it as a test of the no-hair theorem from black holes, that they're fully determined by just mass and spin. So yeah, we'll look at it better. I'll bring the dirty data.
Sorry, I didn't get this thing about averaging for getting the T mu of the gravitational waves. Can you say it again? So what you are averaging on what and why? So what's the bracket that you were using? So
Yes,
I missed that.
It's a space-time average. The idea is that so if you have a smooth background with gravitational waves on top, you want an average that smooths out the gravitational. So if you take an average of this, you get just the smooth part. If you take an average of a quadratic functional of the gravitational waves, you get something which is not zero. It doesn't average. So the gravitational waves in metric, they average out and they just give you the background. But if you average a quadratic potential, it doesn't go to zero, and that's your momentum energy momentum tensor. But still, the presence of the background metric means that geometry is curved, so that's what you use to do your covariant derivatives, your integrals, and so on. So it's by this separation of length scales, it lets you split the signal in two parts, and there's one part that you can treat as a source for the other one. So that's the background. So if you average out, you get the background, but you also get depends what you average. Okay, so but you also get the energy momentum tensor. In is that correct? Yes, because the Einstein because you want also to solve the Einstein equations on the average. So I can bring out the original papers, which are Isaacson with 66, 67, and they're more sophisticated than this, and it's an actual mathematical expansion that keeps track of the orders and corrections and so on, and would define the covariant derivative and all that. But it makes for a nice picture. So yeah.
More questions? So we thank Michele for his lecture. And see you next Friday.
But in practice, you actually never do the average. You just throw away all the divergence pieces by saying, oh, we take the integral. Those are going to be we take them to be zero on the boundary, and so you things that are oscillating. You say, okay, we take we take n wavelengths and just do. There's also a spatial average, but that's a different thing. I mean, yeah. Yeah, but if it's monochromatic, it's really one cycle is the same, is the same as many, right? It's, as long you just take an integer number of cycles. So, yeah, yeah, like that. Yes, but yeah, yeah. But I when people do it carefully, they take this Gaussian smoothing functions and they just convolve them with the waves, and again you get more or less the same.
Just two waves, not the very different reference after a course. That would be example.
On top of each other.
And
Yeah, it's all linear. It's all linear. Yeah, it's all linear. So why not? The interaction will be very small. And yeah, I've never done it in practice because you just take you just take the formulas that that assume this. So it's a foundation in this sense. But I think it makes sense, and we all these things when you dig, you can spend some time to justify it mathematically, and hopefully it works. Anyway, you're free.